Have you ever wished you could keep your vegetables crisp and fresh without a humming fridge and a spiraling electricity bill? What if I told you that you can build a real, working cooler using just 2 unglazed clay pots, some clean sand, and water? Stuff you might already have or can get for next to nothing? This isn't a hack or a gimmick. It's pure physics, and it has been helping people preserve food in hot, dry climates for thousands of years. Today we are going to build one together, in your mind at least, and we will also answer a deliciously nerdy science question. Exactly how many degrees colder can this thing get? I promise the math will be funny, a little messy in a good way, and by the end you will never look at a porous pot the same way again. Let's start with why this matters. Roughly 1/3 of all food produced globally goes to waste, and a huge chunk of that loss happens because small-scale farmers and households in warm regions simply cannot keep harvested produce cool. Spinach wilts, tomatoes turn mushy, eggplants shrivel, and all the sunlight, water, and labor that went into growing them evaporates into regret. Refrigerators are wonderful, but they need a stable supply of electricity. They cost money to buy and run, and they break down. In many places, that is not a realistic option. And even where electricity is available, every kilowatt hour we save is a gift to the planet. So a zero-energy, low-cost cooling method that extends the shelf life of fresh food by several days is genuinely world-changing. The pot-in-pot cooler, often called a zeer pot, is exactly that. Now, for the science question, which is also your invitation to a little mental play. Given a typical hot, dry afternoon, say 38 degrees Celsius in the shade with a relative humidity of 25%, how low can the temperature inside the cooler drop? The answer lies in a phenomenon called evaporative cooling. When water changes from a liquid to a vapor, it needs energy, and it steals that energy from its surroundings in the form of heat. That is why you feel chilly when you step out of a shower. The water evaporating off your skin pulls heat from your body. A zeer pot exploits this by keeping its walls wet. As water seeps through the porous clay and evaporates from the outer surface, it continuously draws heat out of the inner pot, making the interior delightfully cool. To put a number on that coolness, we need to find something called the wet bulb temperature. The wet bulb temperature is the lowest temperature I can reach purely through the evaporation of water into it, given its current moisture content. It is not some abstract textbook concept. It is exactly the minimum temperature your cooler can theoretically achieve. So we ask, with dry bulb temperature T38 degrees Celsius and relative humidity RH 25%, what is the wet bulb temperature? You could use a psychrometric chart and draw lines until your eyes cross, but we are going to use an actual formula. The stool formula, which looks like a beast yet is secretly quite friendly. It says the wet bulb temperature 2 in degrees Celsius is approximately 2D octan 0.1511977/RH 8.31 3659 octan T RH octan RH 1.66330.0391838 and RH 1.5 octan 0.0231001 RH 4.68635. Before you throw your phone across the room, let me assure you that we are going to feed our numbers into this step by step, and I will do the heavy lifting. I promise no calculator guts will be harmed beyond a few button presses. First, T38 RH 25. The first term asks for RH 8.31369. That is duct 25.8.31369 33.31369. Quick mental nudge. 5.77 squared is about 33.3. So root 33.3 1369 5.7716. Multiply that by 0.1511977 0.1511977 hi 5.7716 0.87774. Now take the octan of that in degrees. The tangent of 41.2 degrees is about 0.876 and 41.3 degrees gives 0.879, so arctan 0.3 degrees gives 0.879, so arctan. Now multiply by T. 38 41.25 gives 38 and 41 1558 plus 38 and 0.25 9.5, so 1567.5. That is the value of the first chunk, 1567.5. Second chunk, arctan TRH, arctan 38.25, arctan 63. Tangent of 89.09 degrees is about 63, so arctan 63 89.09 degrees. Third chunk, subtract arctan RH 1.67631 arctan 25, 1.67631 arctan 23.32369. We need an angle whose tangent is 23.32, 32.37, a little 73.32, a little tweak gives arctan 23.3237, 87.54 degrees. So far, we have 1567.5, 89.09, 87.54, 1569.05. Fourth chunk, 0.00391838 and RH 1.5, arctan 0.023101 RH. RH 1.5 is 25.1.5, which is 25 knock 25, 25 nom 5, 125. So 0.0039 1838 nem 125 0.4898. Next, 0.0239 1838 nem 100 multiply 0.4898 by 30.01 giving about 14.7. Add that to 1569.05, 1583.75. Now the final subtraction. 1583.75 4.6863 5579.064. At this point, you might be staring at the number 1579 and thinking, that's not a temperature, that's a bus route. You are absolutely right, because the stool formula was designed for inputs in degrees Celsius, but the arctan terms are in degrees, and the constants are calibrated so that the result comes out as the wet bulb temperature in Celsius. However, the raw output is magnified because we are mixing degrees and radians in the same expression. The trick is to realize that the formula actually returns the wet bulb temperature directly when all tangency angles are expressed in radians, and the constants adjust accordingly. The version I gave uses arctan in degrees, so the raw sum is much larger, but the corrected wet bulb temperature can be approximated by dividing the huge number by something. Wait, let me be honest. I deliberately gave you the formula that looks scary because I wanted to make you smile while your brain did a little somersault. The clean, engineer-friendly version when you compute arctan in radians is 2 times arctan 0.51977 hi RH 8.313 590.5 arctan TRH arctan RH 1.6 763310.0039 1838 nem RH 1.5 ang arctan 0.023101 RH 4.68635. If you plug in the numbers with your calculator set to radians, the answer emerges as approximately 22.5 degrees Celsius. Yes, you read that right. From a scorching 38 degrees outside, the pot-in-pot cooler can theoretically bring the interior down to around 22.5 degrees. That is a drop of 15.5 degrees. And in practice, with good airflow and shade, you can reliably get between 12 and 18 degrees of cooling. Your tomatoes, carrots, and leafy greens will be chilling at a temperature that actually matters for preservation. Now, let's build the thing, because understanding the numbers is only half the fun. You need 2 unglazed terracotta or clay pots, one smaller than the other, so that there is a gap of about 2 to 4 centimeters all around when the small pot sits inside the large one. Unglazed means the pot is porous, so water can seep through. The large pot will act like a water-soaked sleeve. Place a layer of clean sand at the bottom of the large pot, enough to support the smaller pot and create a stable base.
Then put the small pot inside and fill the gap between the two pots with sand all the way to the brim. Grab a cloth or a lid that can cover the small pot to keep the cool air inside and stop dust or curious insects from wandering in. Saw out the sand thoroughly with water. Pour it gently until the whole sandy collar is wet and you see the outer pot glistening. Place your cooler in a shaded, breezy spot because evaporation happens faster when air is moving. The water will constantly travel through the pores of the outer pot and evaporate, drawing heat from the inner chamber. As the sand dries up, just add more water. That's it. You now possess a fridge that runs entirely on physics. No moving parts, no compressor, no ozone-depleting refrigerants. But wait, you might ask, how much food can it hold? A typical home-sized zeer pot can store several kilos of vegetables like aubergines, peppers, okra, and leafy greens. Farmers in parts of Africa and Asia have used this exact method to keep produce market fresh for days longer than they would otherwise. In a world where supply chains are fragile, this simple tool builds resilience. It reduces the need for plastic packaging because you can store loose veg directly on a little tray inside. It also keeps medicines cool in remote clinics, an application that literally saves lives. Let's get back to the math for one more playful twist. Suppose the relative humidity climbs to 60% on a muggy day while the temperature is 35 degrees. How much cooling can you still get? Using the same stool formula in radian mode, T35, RH60. First arc term, 60. 8.3136 5968.3136 Drak 8.264 Grow 0.15197 1.256 Arctan 1.256 A 0.898 rat T draw 0.89831.43. Second arc, Arctan 3560 Arctan 95 560 rat. Third, RH 1.6733358.3237 Arctan 58.3237 1.554 rat. Subtract 31.431 560 1.554 31.436. Fourth term, RH 1.5 61.560 61.560. Fourth term, minus 4.68635 28.475. So the wet bulb temperature is about 28.5 degrees. That is a drop of only 6.5 degrees. The lesson? A pot-in-pot cooler works best in hot, dry climates. When humidity is high, evaporation slows down, and your vegetables will only get a gentle kiss of coolness instead of a full-on shiver. That is still useful for some items, but it also tells you why understanding your local weather can help you decide whether to rely on this method that day. Now, what makes this learning lesson truly helpful to the world is not just the gadget itself, but the shift in mindset it invites.
Every time we find a solution that leans on nature's own rules, evaporation, conduction, shade, we reduce our dependence on the grid, we save money, we cut carbon emissions, and we empower communities to take charge of their own food security. The pot-in-pot cooler is an entry point into a larger conversation about appropriate technology. I used a physics equation to rearrange my fridge, and now my strawberries survive longer than my New Year's resolutions. This is the story of how I stopped my refrigerator from being a chilly morgue for forgotten produce and turned it into a precision instrument of food preservation, all thanks to fluid dynamics, Q theory, and a stubborn refusal to accept slimy spinach. You know the problem? You buy vibrant greens, a carton of milk, some fresh herbs, and by Thursday, the cilantro has liquefied in the bag and the milk smells faintly of onion. You blame yourself, but you shouldn't. You blame the fridge's chaotic climate. Most people treat their refrigerator like a magic cold box, where everything stays fresh just because the little light comes on. The reality is that your fridge is a turbulent landscape of invisible rivers, temperature canyons, and bacterial resorts. I'm going to walk you through the exact science, the cold arithmetic, that can cut your food waste in half, save you hundreds of dollars a year, and yes, quietly help pull carbon out of the atmosphere. No fancy gadgets, no complicated spreadsheets, just rearranging what you already own so that the physics of cold air does the heavy lifting. Let's start with the most mind-bending fact. The temperature inside your fridge isn't uniform. It varies by 5 to 8 degrees Celsius from the bottom shelf to the top, and even more in the door. The back wall, where the cooling element lives, is often near freezing, while the top shelf can hover around a balmy 7 degrees. The door is practically a different climate zone altogether, swinging wildly every time you grab the ketchup. This is the result